We are now going to get into some more complicated problems with forces. And as always, if you enjoy this content, be sure to like and subscribe. So this is going back and looking a little more in detail at blocks on an inclined plane. So this is sort of a common question that often comes up, which is if you have a ramp at a certain angle and you have this block on the incline, what happens if we start to make the angle steeper? So what I did was a free body diagram for both of these situations. And the question says, as theta increases, what happens to Fg, the weight, the force of gravity in the x direction, the force normal, and mu, the coefficient of friction. So let's first take a look at Fg. Fg is the weight, so that's mass times 9.8 meters per second squared down. So no matter what the block is on, if the ramp gets steeper, the force of gravity, the weight, remains the same. What happens to Fgx? Well, Fgx is the component of Fg that's acting parallel to the plane. As the plane starts to get steeper, more of Fgx starts to act down the plane. And we can see that Fgx gets larger in this diagram. Eventually, if the plane got so steep that it was vertical, all of the component would be acting down, and Fgx would actually be equal to the weight. What happens to the force normal? Well, we know in this case the force normal is equal to the y component, or Fgy. Now, if it was on a flat surface, Fgy would just be Fg, and they would be equal. So in this case, Fgy, this component, is still very large because theta is small, so the force normal is large. But as we start to tilt it steeper and steeper, as theta grows, Fgy, which is Fg cos theta, is going to get smaller. And because it's getting smaller, the force normal goes down. So Fgx, we said, goes up, Fn goes down. This is a trick question. What happens to the coefficient of friction? Coefficient of friction is only a measure of the slipperiness of the surface. So that depends on the surfaces themselves, and the surfaces aren't changing, so the coefficient of friction is remaining the same. So let's look at a slightly more tricky set of questions. If it says how much force of friction is required to hold it in place, well, that means that the net force would be zero. And if the net force is zero, then the acceleration would be zero. And if the object was at rest, it would stay at rest. So this value of friction would be exactly the same. Now we have to be careful, because if this was static friction, which is holding it in place, the static frictional force would be equal to Fgx, but we could not use Ff equals mu SF Fn, because this only calculates the maximum value of friction, and this value might be below that value. This would be exactly the same in this diagram. The force of friction to hold this in place would have to be equal to Fgx. The next question says, how much force of pull up the plane to create constant velocity? Well, if we're going to drag it up the plane at a constant velocity, let's say there's no friction in this case, then these forces would have to be equal. So the force of pull would be equal to Fgx, or the force of pull would be equal to Fgx. And the last question says, how much force of push or pull up the plane to make it accelerate up the plane? So in that case, we would have to have, if there's no friction, Fp would have to be larger than Fgx. And here again, Fp would have to be larger than Fgx. If there was friction, the force of pull would have to be larger than Fgx and force of friction combined. So if we had a force of friction here, and we wanted it to accelerate up the plane, Fp would have to be larger than the sum of Ff and Fgx. This is an interesting problem. Let's say we have a block. It could be a book or something like that. And we push the book against the wall. And we push it so hard that the book just remains motionless. In other words, it doesn't slide down the wall. Now, what would keep it from sliding down the wall? Well, that would be the force of friction pushing up due to the force between the block and the wall. Well, what's providing the force normal in this case? Well, the person pushing on the book pushes the book against the wall, and the wall pushes against the book. That force of the wall pushing against the book is the force normal. So let's look at the question. The block is pressed against the wall with a force of Fp. That's going to be this force here. What's the minimum coefficient of friction to hold this book in place? Well, our Fn is going to be equal to our Fp. We have a force of friction up that's going to be equal to the force of gravity down. These forces cancel each other so that the book can remain motionless. So we write an F net y equation. We have Ff up and Fg down. So that's Ff up and Fg down. And we know that Ff is mu Fn. But remember, Fn in this case is equal to Fp. So we can sub in Fp for Fn. Solving for mu, we would just divide through, and mu would be equal to mg divided by Fp. And because it's not moving, that would be static friction. In this next question, we have two blocks connected by a cord, and the mass 2 has a force of pull on it, and we're saying that there's no friction anywhere involved. So we know that this system is going to accelerate. And the question is, find the force of tension between these two blocks on this cord right here. So what we can do in this problem is solve it as a system. In other words, take everything at once and analyze all of the forces. So what forces do we have acting on it? Well, we're going to say that we have F net equals m1 plus m2, because it's a system, times A equals, and what forces are acting on m1? Well, there's the force of tension. We're not dealing with the y direction, we're only dealing with the x. So that's just going to be force of tension 1. Block 2 is going to have a force of tension in the opposite direction, so that's going to be negative Ft2. Now, these two forces are equal and opposite. They're a Newton's third law pair, so these are going to cancel out to 0. And then we have force of pull, and that's acting on the entire system. So that just becomes Fp. So what's next? Let's find out the acceleration of the system. Well, the acceleration is just going to be m1 plus m2 divided to the other side, so that's going to be Fp divided by m1 plus m2. So now to find the tension, we can do this by either analyzing just block M1 or just block M2. But it's easier to do this on block M1 because there's only one force. On this block, there's two forces. But either way, we would get the same answer. So let's do a net force equation on block 1. So that's going to be M1A equals force of tension. We know the acceleration now, so we can say m1 times Fp over m1 plus m2, and that's going to be equal to force of tension. Here's another question that comes up frequently, which is, if we have a force of tension acting on a string of blocks, then we're going to have tension in each string. And the question is often, which force is going to be the largest of these three? Well, if you think about it this way, this force of tension only has to act on block M1. Force of tension 2 has to pull both blocks, and force of tension 1 has to pull on all 3 blocks. So force of tension 1 ends up being the largest force. This problem is very similar to the last problem. Instead of having a cord in between the two of them, we're going to be analyzing the force of how much block 1 pushes on block 2 and block 2 pushes on block 1. So we have 2 blocks, there's no friction, and the force of push is going to be a constant push. So it pushes on these 2 blocks and it's going to accelerate them. But what we can do is treat block M1 and M2 as if it's one block. So really what we're doing is we're saying force of push on the combination of M1 plus M2. I'll call to the right positive and to the left negative. The question is, how much does mass 2 push on mass 1? So to be able to do this, we're going to start by solving for the acceleration. So to do that, we have M1, so we're going to do F net, equals M1 plus M2 all times A, and that's going to be equal to just Fp. So what is the acceleration? The acceleration is just Fp divided by M1 plus M2. So now we can solve for the force on block M2. So block M2 only has one force on it. It's the force of block 1 pushing on block 2. So that I'm going to call force 1 on 2, block 1 on block 2. So what's that going to look like? That's going to be F net equals MA, and in this case it's M2, equals, and then it's going to be force of 1 on 2. And we know the acceleration from the part before, so that becomes M2 times Fp over M1 plus M2 equals F1 on F2. Whoops, F1 on 2. I'm just writing it as on 2. Now, the question was, how much does mass 2 push on mass 1? Well, these are equal and opposite forces. So how much does F2 push on 1? That's just going to be negative M2 Fp M1 plus M2. This problem is called an Atwood machine. And what it consists of is a massless, frictionless pulley in which we have one mass hanging on one side by a cord and a second mass hanging by a cord on the other side, and the cords are massless. So as you can see, if M2 is larger than M1, then M2 is going to accelerate down and M1 is going to accelerate up. But we can think of pulleys as objects that change direction. So if this is down and it's accelerating down, we can call that positive. But the acceleration on the other side will be up, so up on the other side will be positive. So it's as if plus gets changed by the direction of the pulley. Plus down on this side, plus up on the other side. So if M2 is larger than M1 and we have an acceleration up, the forces on M1 are going to be the force of tension 1 up, which is going to be larger than the force of gravity, the weight on block 1, so that it accelerates up. The Ft2 is an equal and opposite force pair. That's Newton's third law. So these forces are equal and opposite. And then lastly, we have Fg2, which is the weight of the second block, and that's going to be acting down, and it has to be larger than Ft2 to have a downward acceleration. Again, these two look as if they're both up, but this one is up in the positive direction, and this one is up in the negative direction, so these are opposite. So now we write our F net equation to solve it as a system. So that's going to be F net equals M1 plus M2 all times A, which is equal to, and now we add them up. We have a minus Fg1 we have a plus ft1, a minus ft2, and a plus fg2. Now, because ft1 and ft2 are equal and opposite, those are going to cancel out. So we're left with m1 plus m2, a, equals, and then we have minus fg1, so that's going to be minus m1g plus m2g. Oh, I crossed that out here. That should have been like that. M2g. So now we can solve for acceleration. So acceleration, I'm going to switch these and say m2g minus m1g. So that becomes m2g minus m1g, subtracting, dividing through by m1 plus m2. So now we have an expression for the acceleration. But the question was also to find the force of tension. So to find the force of tension, we're going to write an F-net equation, but this time we're only going to write the F-net equation on M2, because if we do it the other way, the forces of tension cancel out. So in this case, we have Fg2, which acts down, so that's positive. And here's a tricky thing that a lot of people have trouble with. I'm going to put in Ft2 as positive because Ft2 is our unknown. So if we want the equation to predict the direction, we leave it as positive to let the equation let us know if it's negative. So now all we have to do is sub in the acceleration that we had before, and I'm going to factor out the g, so that becomes g. And then on the top, that gives us m2 minus m1 all over m1 plus m2. And then equals, and on the other side of the equation, we have m2g plus ft2. And if we subtract this to the other side, that gives us m2g, m2 minus m1 over m1 plus m2 minus m2g, and that's going to be equal to ft2. And we can factor out our m2g and rewrite this as m2g, the quantity, m2 minus m1 over m1 plus m2, and all of that minus 1. This problem is similar to what we've been doing, except this time we've got angles involved. So we're going to say, to make this a little simpler, that m2 is much larger than m1, so that we know that the acceleration will be like this. m2 will accelerate down, and m1 will accelerate up the plane. So I'm going to call plus in the direction of acceleration. So the question is, find the acceleration. Well, we're going to do the same thing that we've done before. The difference in this problem is that we have a force of tension up here, and this is not going to be the force of gravity, this is going to be a component. So if we divide our forces up and we have Fg down, then the component that's acting down the plane is going to be Fgx, which is going to be Fg sine theta or m1g sine theta. Then we have force of tension acting up. If it's accelerating up the plane, Ft1 has to be larger than Fgx. Looking at block 2, we have Fg2 down, which is larger than the force of tension up. The force of tension up here has to be equal to the force of tension up the plane here. These are equal and opposite forces. So again, we're going to do this as a system first to find the acceleration. So we say F net equals m1 plus m2 all times a. and that's going to be equal to, and what is FGX? Well, that's our opposite side, so that's going to go with sine. So that's going to be negative m1g sine theta. Now, our force of tension here is going to be plus Ft1, and our force of tension here, down is positive, so up is negative, is going to be minus Ft2. And then finally, we have plus Fg2, which is just going to be m2g. Now, if we know that these are equal and opposite forces, they cancel out to 0. And we can factor out a g on this side. So we end up having A is equal to g m2 minus m1 sine theta all over m1 plus m2. I just rearranged the plus and the minus and flipped them there. So if they asked us to find the tension, the easiest way to do this would be on block 2. And what we would do is we would say F net equals MA, and we would do this on block 2. And then we would say that we have the force of tension up, which is negative, so we leave that as positive because it's our unknown. And then we have Fg2 acting down, which is just Fg2. And then we would take this acceleration, sub it in, and solve for Ft2. Let's try another problem. This one where we have a block on a surface, and this time there is friction. Now, if there's friction, then we have an additional force acting to the left. And in this case, it says it's being dragged along at a constant velocity, and find mu k. So this one's a little bit different. When we write our F net equation, the acceleration is going to be 0, so this whole side is going to drop out to 0. If it's constant velocity, then the net force is 0 because the acceleration is 0. And then what forces do we have acting on the object? Well, we have the force that's acting this way, which is going to be friction, so that's minus FF. Then we have the force of tension acting this way, that's going to be plus Ft1. Then we have the force of tension acting up on block 2, that's going to be minus Ft2. And then we have the weight of m2g, so that's going to be plus m2g, the force of gravity on the second block. So this drops out to 0, and these two forces drop out to 0. And what that does is it leaves it saying that FF, I'm adding FF to the other side, is equal to m2g. Well, we know that the force of friction is mu Fn, and that's going to be equal to m2g. But the force normal on a block that's just sitting on a flat surface is just equal to its weight. So Fn up is equal to m1g. So this becomes mu m1g equals m2g. And we have a g on both sides, so we can cancel them out. And we're left with mu is equal to m2 over m1, and because it's sliding, this means it's kinetic friction, so that's mu k. In this problem, we have a block like we had before, 2 blocks and a pulley, and the question is to find the acceleration and the force of tension. But this time we're not going to do it as a derivation, we're going to do it with numbers, and there's something added that makes this much more difficult, and that is there's friction. So we have a kinetic friction of mu k 0.1. The problem is we don't know which way it will accelerate. It's possible that this could accelerate like this, where this accelerates up the plane, this accelerates down, but also if the other components were larger, we could have it go this way. Well, if it accelerates up the plane, friction acts that way. which means we have to put that into our net force equation with the correct direction. But if it accelerated the other way, then friction would be acting in the opposite direction, and we would have to take that into account. So there's two different methods for solving this. One is to do the whole problem and find out what sign friction comes out as. But what I prefer to do is to just see which is larger, the m1g sine theta or the m2g. And I'll explain this. If there was no friction, we know that the force of tension here and the force of tension here would cancel out. So really this becomes a tug of war between m2g and the component of this, which would be m1g sine theta. So which is larger? Is m1g sine theta larger, or is m2g larger? So let's go ahead and find out. So we can say m2g is equal to, and that's 3 times 9.8, which is equal to 29.4 newtons. And m1g sine theta, that's going to be 5 times 9.8 times sine 30. And the value for that comes out to 24.5. So what does this tell us? It tells us that this force acting down is larger than the component force of gravity acting this way. So the system will accelerate like this. Now, why do we need to know that? Because that tells us that friction is acting in this direction. Now we know what sign friction is going to be in our net force equation. So we can say, so friction acts down the plane. So let's go ahead and set up our F net equation as a system. So as a system, we have F net equals m1 plus m2 all times a. And what forces do we have acting on it in this plane? Well, we have m1g sine theta, the component of fgx, component of fg, which is fgx. We have friction acting down the plane. We figured that out. We have tension acting up. And the force of tension acting up is larger than the sum of these two forces, so that there's an acceleration in this direction. And over here, we have fg2 acting down, which is larger than ft2 acting up because the acceleration is down in this direction. So what forces do we have? We have minus ff minus m1g sine theta plus ft1 and minus ft2 and plus fg2, which I'm going to put in as m2g. These forces are equal and opposite, so they cancel each other out. And then we have an added little problem. And that problem is that we need the force normal. Because what we have here is the force of friction. And force of friction is equal to mu Fn. So what's Fn in here? Well, it's going to be minus mu, and then it's the component of gravity acting down the plane. So that's going to be m1g cos theta. So that's mu m1g cos theta. And then we have our minus m1g sine theta and our plus m2g. So let's put in our numbers. We have 5 and 3, so that's 8a. And then we have our coefficient of friction was 0.1, 5, 9.8, cos 30, minus m1, which was 3 times 9.8 times sine 30. And then finally, oops, nope, that's 5, because that's still mass 1. And then the last one is mass 2, so that's plus 3 times 9.8. And if you add those all up, you get 8a equals 0.66, or a equals 0.08 meters per second squared. It came out positive, which agrees with what we expected, which is that block M1 will accelerate up the plane and block M2 will accelerate down the plane. And finally, we have to solve for the force of tension. So we can do that on either block, but block 2 doesn't have any angles, so let's do it on block 2. And we have F net equals ma. What forces are acting on block 2? Well, we have m2g down, and our unknown force of tension, which is acting up in the negative direction. But again, we'll put it in as positive to let the equation determine the sign for us. So that becomes 3 times 0.08 equals 3 times 9.8 plus ft2. And if you do the math on that, you end up getting ft2 equal to negative 29.2 newtons. The negative sign agrees with what we expected, that the force of tension acts up.